we're going to go through some background information on Profiler to introduce you to the tool. So what is Adreno Profiler? A profiler is similar to other graphics performance analysis and debugging tools you may have seen on other platforms, such as PIX for Xbox 360 or GDEB for PlayStation 3, etc. The profiler documentation or instrumentation has been built into our graphics driver, so the only thing you really need to use Profiler besides getting the tool is a Qualcomm Adreno-based handset. So if you have one, it's built into the graphics driver. You don't need to do anything to modify your application. You can just start it up and start using the Profiler to profile it. So who's using it? Currently, Profiler was designed for 3D content developers. So anybody developing 3D content on one of our platforms, this is a good tool for them to use. We use it internally as well as distributing it to customers and to any third-party content developers. So why use a tool like Adreno Profiler? Well, if you've ever spent time optimizing for GPUs, you know that it can be difficult. There are a lot of different factors involved with optimizing for graphics. There's many. The GPU itself is a complex piece of hardware with many different components. The driver adds another layer of complexity to that. So in finding where your bottlenecks are, it can be really difficult to do that without having some kind of tool to streamline the process. And built into Profiler, we have a complete range of features that allow you to do this. So this includes things like hardware performance counters, metrics you can retrieve on a per-call basis, the ability to edit your shaders in real time, and things like that. And I'll go into the full details of what's involved there. It also allows you to quickly experiment with different changes. So rather than in the typical model of suspecting that your bottleneck exists in a certain place and going and rebuilding your application and redeploying it, which can be very time intensive, you can actually very quickly, using the Profiler, make changes in real time so that you can see what the impact of those changes would be. So Adreno Profiler connects using just a standard USB connection. There's no cost associated with getting Adreno Profiler. It's free to download. You can get it right now from our developer website, which is qdev.net or developer.qualcomm.com. All you have to do is just simply create a profile on there, which is free, and then you can download it. Currently, this is supported on the Brew platform, including BMP, starting now. Windows Mobile 6.1 and 6.5, on all Android platforms, Linux LE, and of course all this is on Qualcomm-based chipsets. The client itself runs on PCs with Windows XP or Windows 7, and it should work on any machine with an OpenGL 2.0 compatible graphics card. So I'm going to go through some profiling techniques, and then I'll go ahead and get into the demo itself. So in profiling, there's basically two steps. You need to discover what your problems are, and then validating what the impact on fixing those problems will be. So the first starts with discovery. So where are the problems in your application? So Profiler includes two different modes to help you identify where your problems are. The Scrubber mode allows you to do really detailed analysis of a single specific call trace. So this would typically be a single frame. Or Grapher mode. And what Grapher mode allows you to do is connect to the hardware counters in real time and monitor those. And I'll show both of these in detail. So like I mentioned, the Scrubber mode allows you to capture an entire call trace. It includes a lot of different features within that. One of them is what we call heat graph mode, which allows you to visualize what the most expensive calls are based on various hardware metrics. You can also visualize the amount of overdraw you have. We use a tile-based binning architecture for our GPUs, so you can see what those look like. You can see how bitmaps are being used. You can override shaders. You can inspect the alpha color and depth channels. And then you can do specific optimizations generated from your call trace and a lot of other things. In the Grapher mode, you can plot a number of different metrics that are captured in real time from the device. This includes, of course, frames per second, how well are you using GPRs, and if it's stalling based on those, various CPU statistics, and a lot of different GPU statistics. In addition to that, in conjunction with those metrics that you're monitoring, you can apply overrides in real time and see what kind of an impact they have on those metrics. So for instance, you can disable pieces of the pipeline or force certain states and see what kind of an impact that has on your frame rate. And so then after you've discovered what your problems may potentially be, the next step is to start to make some changes and see if those actually improve your performance. So just finding where your problems are is just half the battle. It may turn out that the cost associated with fixing that particular problem outweighs the potential benefits you get from that. So Profiler can help you understand in advance how much you gain from actually fixing that problem. So for instance, if you identify early on in the process that you're CPU bound, spending a lot of time on GPU-specific optimizations isn't going to save you anything because the benefit of those will never be realized. So one of the tools that Profiler gives you to enable to validate your changes is these overrides. So you can very quickly turn features on and off and see what kind of an impact they have on performance. So using these overrides in combination with the graph remote gives you a really quick and powerful way to test out your changes. So with that, we'll go ahead and go straight into the live demo, and I'll go through and show you in detail everything that's involved with Profiler. So you should all be seeing Profiler now. So I'm going to go ahead and start an application on a device here and connect to that. So what I've connected to is an application called Robust, which is an OpenGLES 2.0 based benchmark that we developed. So the first thing I'm going to do is create a scrubber window. As I mentioned, the scrubber mode is what allows us to do a detailed analysis of a single call trace. So I'm going to go ahead and capture a frame. So this takes a few seconds, but what happens here is within the OpenGLES driver, we've introduced a shim layer, which allows us to intercept all of the OpenGLES API calls. And so not only are we able to capture the calls themselves, we capture all the parameters and all the data associated with those calls. So what that allows us to do is to recreate the scene on your PC using our OpenGLES 2.0 emulator. And through doing this, we're able to allow you to provide have really detailed analysis of what's going on in that frame, look at all the individual calls and all the states associated with that. And so that's what you're seeing here. So let's take a look at this. The first thing I want to draw your attention to is down here at the bottom in the comments panel. So the first thing we do is, since we've found that a lot of people run into the same kind of issues over and over in developing graphics application, we look for some of the most common mistakes that people make in analyzing the call trace, and we identify those. The first thing you want to do when optimizing your application is look through this and see the suggestions we have for things that you might want to improve. Now, some of these will be marked as more serious things, like you see the red X thing here, and then there's informational warnings as well. But by looking through these, you can kind of just do a quick sanity check to make sure you're not doing anything really bad right off the bat and start working on fixing those things. The next thing I want to draw your attention to is the call trace over here. So by clicking on these, you can actually step through the individual draw calls. And as you move through the list, they're highlighted in the scene so you can see what's being drawn on that particular call. And if you go through all these, you can see the scene being recreated in full. Now let's jump down to the end there. In addition to seeing the draw call itself, there are other pieces of information associated here. So you can look at the API calls to see all of the other OpenGLES API calls that were made between the current draw call and the previous one. In addition to just showing those, we identify some special ones, ones that have no effects. So these are OpenGLES API calls that, for instance, would change a state to a value that it's already set to. We also look for heavyweight API calls. So there were some of those back near the beginning. And this includes things like setting a vertex buffer object for loading textures and things like that. Typically, you'd want to only see those once per frame at most, which is what we have here. But if you're having a lot of those throughout the frame, it would be an indication that perhaps that's something you could offload to load time or something like that. In addition to viewing all the API calls, you can see all of the OpenGLES context state settings for at that particular moment. And then we also provide a complete set of frame stats. So, for instance, the total number of API calls made, average number of triangles, and things like that. So currently we're viewing the scene in the color buffer for the scene. In addition to that, you can also view the depth buffer. You can view the stencil or alpha buffer if there are those. In this case, there's no stencil buffer, and here's the alpha channel for the color buffer. If you're using frame buffer objects, you can toggle whether you're viewing the current FBO or the frame buffer at that particular time. I mentioned that our GPU uses a binning architecture, so this allows you to visualize on screen where those bins actually lie. So there's some applications where you might want to optimize and override the built-in binning mechanism and take control of that yourself, and this would allow you to kind of see on the screen where those bins fall so that you could potentially do that. Currently viewing it in fill mode. You can also view the scene in wireframe mode. And then, as I mentioned in the introduction, there's several different overdraw modes. This gives you an idea of how effectively you're using your depth buffer. So the areas that are white are areas that are getting drawn to repeatedly, so you can potentially do optimization to reduce that if you're seeing a lot of white areas on the screen. And there's also some convenient things like you can rotate the scene and either fit it to the window or show it at the original size. As I mentioned, in addition to capturing all the draw calls, we capture all the data associated with them, so that allows us to grab all the textures that are in the current scene. So as you step through this list and you select the texture, it gets highlighted where it is in the scene. And down here you can view the texture directly. So if there's bitmaps, you'll view those. Otherwise, it'll just show the base texture. And there's a few things you can do here. If it's a texture with an alpha channel, you can view that. You can, for bitmaps, override the bitmaps with solid colors. So this would allow you to view how effectively you're using bitmaps in a large scene. In addition to just using the default texture, you can override it with the texture from a file. So if you wanted to just preview it within this window how a different texture might look, you can do that. And then you can take the texture that's been retrieved from the device and save it off to a file. In addition to grabbing textures, we also grab all of the program objects. So you can view those all here. So it's grabbing all of the program objects for the current context, not all of which are being used at a given time. So the ones that are shown in red are objects which are loaded but aren't currently being used. The black ones are the ones being used. So if you click on those, you can see where they show up in the scene. So this is the robot shader here. And in addition to viewing just like the general information about that, you can actually pull up the shaders themselves. So I'm looking at the vertex shader here. I'm going to switch to the fragment shader. So I'll get into the shader code itself in a minute. In addition to just showing the shader, we run a shader analyzer on it. So this provides a lot of statistics about that shader. So you can view this here and scroll through this, but it shows that the shader uses 4 GPRs, 11 ALU instructions, 3 texture instructions. So you can get an idea of how expensive that particular shader is just through looking through the analyzer frame. And then you can look at the source code to the shader itself here. The interesting thing about that, as I mentioned, is that not only can you view it, you can actually modify your shader and load it to the device in real time. So I'm going to go ahead and do that here. What I'm going to do is replace the final color that's calculated with just a solid color. So I'm going to change this so that it's just writing out fuchsia. And if I switch that, you can see in the scene now the robot's being drawn that way. But not only can I change it within the emulator preview here, but I can actually use the send button, and this will send it to the device. Now, people on the call can't see the device, but the robot is now being rendered in real time as pink. So that particular change isn't practical or particularly useful, but what this illustrates is that if you want to optimize your shaders, typically what you have to do is, make changes to the shader, rebuild the application, redeploy it, and see what kind of an impact that has. This allows you to greatly streamline that process, because instead of doing all that, you can just simply load your shaders into here, make your changes here, and immediately see what kind of change they have, not only in performance, but in actually how it looks on the device. So this really greatly streamlines the shader development process. And then if you want to revert to the original shader, you can just use this button, and it will restore the shader to its original state. And then if you want to take your shader and save it off to a file, you can do that using export shader to a text file. The last thing that I want to show you in this mode is the ability to view some metrics. So there are several metrics which we make available in this mode. You'll notice that a lot of things in Profiler, we provide documentation in the tool itself to give you an idea of what that actually means. So if you look at the metric list and click on a specific metric, you can see this tooltip that pops up that shows you what that actually means. To sample this metric, I can just grab it and drag it onto the scene. And now what I need to do is recapture that frame. So I'll go ahead and do that. And what this is doing is now when it makes as all those draw calls are being made, it tells the GPU to track that particular metric and see what the cost of that particular draw call was. So this adds a new column now to the call trace that shows you that clocks metric. And you can see that visually here. So the ones that are green are ones that have a lower, they use fewer clocks than the ones that, say, have red. But in addition to just viewing that here in this mode, you can actually click on that, and then it re-renders the scene using color code based on that particular metric. So with this, you can really quickly see what the most expensive parts are in the scene when it comes to that particular metric. And you can actually do that with a lot of different metrics and sample several at once, so that you can really quickly just visually see what the most expensive part of that particular scene are and potentially optimize that. So for instance, if you had something that's doesn't significantly contribute to the scene, but was being shown as red, you have a pretty good idea that that's something that you could start to optimize. So that's it for the scrubber mode, and I'll go ahead and move now to the grapher mode. A minute for that window to pop up. There we go. And now look at the grapher metrics tab. So there's a bunch of different metrics that are being shown here. As I mentioned, some of these are for the CPU and some are for the GPU. I'll only spend a moment on the CPU-specific metrics, but the first thing I want to pull up is the frames per second. This is generally like the most useful metric that you'll want to take a look at, because it'll give you just a frame of reference for everything else that you do. I'm going to change the frequency with which I'm sampling currently. It's sampling 4 times a second. I'm going to bump that up to 10. So what this is doing is, as I mentioned, there are several hundred different hardware counters that are available in our GPUs. What I'm asking the hardware to do is to sample certain numbers of those counters. We don't expose all 100 of them, because not all of them are really relevant to application developers, but we take those and we distill them down into a subset which application developers might find useful and expose them here. So as mentioned, there are several CPU metrics we make available as well. So I can start to drag those over. So percent of the CPU that the app is utilizing. Our CPU includes a vector coprocessor called Venom. You can sample those metrics as well. And I'll start to look at the GPU metrics. So we'll grab GPU busy percentage. One thing you'll notice here is there's this global button. So what this means is that normally when you're profiling an application, it's looking at metrics related to a specific OpenGLES context. Normally that's what you want, but there are times when you might want to view the entire system. And when that's the case, you can just click on this global tab, and now it'll show the usage of the GPU of your application relative to the entire system. So by definition, a given context is going to use 100% of the resources available to it. And so that will always be 100%. But now that I switched to global mode, you can see that this app is using about 50 to 60% of the GPU's available resources as a whole. I'll switch back to just the specific context. We can view the various GPU stalls that are exposed. So this includes the GPR stalls. So general purpose registers are what the GPU uses to hide latency. And if you have large shaders, you can frequently run out of GPRs, in which case the ability to hide latency is lost. So that's an important metric to keep an eye on. So I'll pull that over. You can also see the percentage of time that the GPU is waiting for the vertices to be fetched or fragments to be fetched. As I mentioned earlier, with all of these, as you click on the particular metric, we provide you with a tooltip that gives a description of what exactly that metric means. In addition to just telling you what it means, whenever possible, we try to give you an idea of what normal values are for that metric, or what a high value might be, and if it is high, we try to provide recommendations for things that you can do to change your application to get it back within an acceptable range. So that's not always possible to accurately predict what changes you're going to have to make to do that, or since a lot of times these valid ranges for these will be highly content dependent, we can't always tell you that, but when it is possible, we do try to provide some hints as to what you can do to get that metric within a desirable range. So as you can see, there's a lot of different metrics that are available here. Some of them start to show up in red as you drag these over. The reason for this is that the metrics, or the metrics that are stored by the hardware are stored into registers, and there's a limited number of register space available. So as you increase the number of metrics that you're sampling, you run out of registers to store those, so certain ones become unavailable. But generally speaking, you can sample quite a lot of registers at once. So I'm going to pull over fragment shaded per second. For pixel processing, you can see things like the average primitive area, number of pixel writes per second, the number of pixels that where depth test failed or where stencil test failed. For vertex processing, you can see the average number of vertices per primitive, the pre and post clips primitives per second. Pre-post clip ratio is a good metric to keep an eye on. This tells you how effectively you're pre-culling geometry. It basically tells you how many triangles there are after clipping versus before clipping. And you want this typically to be very close to 1. If it's a lot higher, it means that you probably can more effectively pre-cull your scene. And then you can also see GPU texturing metrics such as the percent that are nearest filtered, bilinear filtered, anisotropic filtered, and then the number of textures which are coming from non-base levels. So as I mentioned in the introduction, where this gets useful is when it comes to overrides. So overrides provide, so what you're seeing here is these metrics are reflecting the application as it's running in real time. So as you know, the scene changes, you can get an idea of what's the most expensive part of it and use that to start to optimize. But through doing that, you'll start to have guesses about what your most expensive things are. As I mentioned in the introduction, you want to validate those guesses before you start to make changes, since that can be expensive. And to do that, you can start to toggle overrides here in this interface. So there's quite a lot of different things you can toggle. Let's look at some of the more useful ones. So the first one we want to look at is just disabling GL. What this effectively does is it turns off all of your pipelined OpenGLES calls. So this includes all your draw calls, clear calls, and finish. What this effectively does is make the GPU act as if it's infinitely fast. So if you turn this off and there's no change in your frame rate, what that tells you is that you are CPU bound. Because if you suddenly have an infinitely fast GPU and your app doesn't get any faster, that means no matter how much you optimize your GPU-specific code, your app's not going to run any faster. So we'll go ahead and do that. This top metric here is the frame rate. As you can see, it did jump up. So that immediately tells me that this app is not CPU bound, that I'm not wasting my time by looking at graphic-specific optimizations. And in case it's not clear, all of these overrides, these are being done in real time on the hardware. So this is not in any way tied to the emulation being done on the PC. correctly immediately happens on the device. So there's a bunch of other different things you can force on and off. So you can force blending off if you think blending might be potentially a bottleneck. You can force a scissor test reject. So what this will do is effectively make the scene become a one-by-one window. So if you think that your application is some way fragment rate bound, this will quickly tell you that. If you force this and your frame rate goes up, which it did in this case, it tells you that your bottlenecks probably do exist in the fragment stage somewhere. Other things you can force include forcing small textures. This will replace all the textures in the scene with a 4x4 texture. So frequently a problem is that, if your textures are really large and you're swapping them out frequently, texture bandwidth can quickly become your bottleneck. So this will really easily tell you whether or not that's an issue. If you do make this change and frame rate goes up, it means that you can optimize your application by making your textures smaller or using compressed textures or something like that. You can also do various changes in the vertex state, such as forcing culling off, forcing it to reject everything through culling, turning VBOs on and off, and things like that. So through doing all these overrides, you're able to really quickly see what kind of an effect making a particular stage of the pipeline infinitely fast or infinitely slow has on your overall performance. And of course, one other thing I wanted to show here, you can view both of these modes at the same time. So if you wanted to kind of correlate what's going on in your scene with what's going on in the grapher mode, you can see that as well. You can create as many windows as grapher windows as you want, although there's practical limits on how useful that is. But if you had a bunch of different metrics you wanted to view and you couldn't see them all easily here, in a single window, you can break those off into separate windows as well. So I think that's everything I wanted to show. So this is, as I mentioned, so this is currently freely available on the QDevNet website. So you can get this as long as you have a Qualcomm Adreno GPU-based device. You can connect to it and immediately start profiling your application and using this today. So